Mathematicians call that idea infinity. Now here's the strange part. Infinity is something we talk about all the time in mathematics. But when we turn to the real universe, the one filled with stars, galaxies, and atoms, we start to wonder whether infinity actually exists out there, or whether it's just a convenient idea inside our heads. Physicists often run into infinity in surprising places. When equations describing gravity or quantum particles are pushed to their limits, sometimes the numbers explode toward infinity. These moments are known as singularities. One famous example appears at the center of a black hole, where, according to the equations of general relativity, developed by Albert Einstein, gravity becomes so intense that certain quantities mathematically grow without limit. But here's the puzzle. Does nature truly allow something to become infinite? Or is infinity simply a signal that our theories are incomplete? This kind of question fascinated thinkers like Richard Feynman, who loved pointing out that the universe often behaves in ways far stranger than our everyday intuition suggests. Sometimes infinity appears not because reality is infinite, but because we have reached the edge of what our current understanding can describe. So tonight we're going to explore a fascinating paradox. Is infinity something that actually exists in the universe? And paradox, is infinity something that actually exists in the universe? Or is it just a mathematical tool that helps us describe a reality that is always, in the end, finite? When people first encounter the idea of infinity, it often feels simple and almost obvious. If you start counting numbers, 1, 2, 3, 4, you can always continue. No matter how large the number becomes, there is always another number waiting beyond it. This simple observation leads naturally to the idea that numbers never end. They stretch outward forever in both directions, forming what mathematicians describe as an infinite set. But infinity did not always have a comfortable place in mathematics. For centuries, many mathematicians treated it cautiously, almost like a dangerous concept that could easily lead to contradictions. Infinity seemed less like a number and more like a philosophical idea about endlessness. People could talk about something being infinitely large or infinitely small, but working with infinity in precise mathematical ways was considered risky. This changed dramatically in the 19th century through the work of the mathematician George Cantor. Cantor did something that, at the time, seemed shocking. He began to treat infinity as a subject that could be studied rigorously, almost like any other mathematical object. Instead of avoiding infinity, he explored its structure and discovered that it had surprising and deeply counterintuitive properties. One of Cantor's most remarkable discoveries was that not all infinities are the same size. At first, that idea sounds impossible. If something is infinite, how could it possibly be larger or smaller than another infinity? Cantor demonstrated this using simple examples involving sets of numbers. Consider the set of all natural numbers. 1 to 3, 4, 5, and so on. This set clearly continues forever. Now think about the set of even numbers. 2, 4, 5, and so on. This set clearly continues forever. Now think about the set of even numbers. 6, 8, 10, and so on. Intuitively, you might think the set of even numbers should be smaller because it contains only half of the natural numbers. Yet Cantor showed that these two sets actually have the same size of infinity. Every natural number can be paired with exactly one even number. The number 1 pairs with 2, 2 pairs with 4, 3 pairs with 6, and the pattern continues forever. Because every element in one set can be matched with an element in the other, the two infinite sets are considered equal in size. This idea already stretches our intuition, but Cantor went even further. He examined the set of real numbers, which includes not only whole numbers but also fractions and irrational numbers. Between any two numbers on the number line, there are infinitely many additional numbers. The number line is densely packed with values that continue without limit. Cantor proved something astonishing about this set. Using a clever argument now known as Cantor's diagonal method, he showed that the infinity of real numbers is actually larger than the infinity of natural numbers. In other words, there are more real numbers than counting numbers, even though both sets are infinite. This result revealed that infinity is not a single concept, but a hierarchy of different infinite sizes. Some infinities are countable, meaning their elements can be listed in a sequence. Others are uncountable, meaning no such list can ever capture all their elements. The idea of mathematical infinity suddenly became far richer and more complex than anyone had imagined. Cantor's work was revolutionary, but it was also controversial. Many mathematicians initially resisted his ideas because they seemed so strange and difficult to accept. The notion that there could be multiple kinds of infinity challenged centuries of traditional thinking about numbers and sets. Over time, however, Cantor's theory became one of the foundations of modern mathematics. Today, his ideas about infinite sets play a central role in fields ranging from analysis and topology to computer science and logic. Yet even as mathematicians became comfortable working with different forms of infinity in abstract systems, a deeper question remained unresolved. Mathematics allows us to describe infinite sets and manipulate them with remarkable precision, but that does not necessarily mean infinity exists in the physical universe. Numbers can extend infinitely in theory, but the universe itself may or may not share that property. The cosmos could be finite in size, or it might stretch endlessly beyond the limits of observation. This distinction between mathematical infinity and physical reality becomes one of the most intriguing philosophical questions in science, because while mathematics freely explores infinite structures, physics must eventually ask whether the universe truly contains anything that is infinite, or whether infinity appears only in our equations when we reach the edge of what our current theories can describe about the nature of reality in a cosmos that may be vast beyond imagination, yet still fundamentally limited by laws and structures that prevent anything from actually becoming infinite, the way mathematics allows within its abstract world of numbers and sets, where infinity remains both a powerful tool and a profound mystery waiting at the boundary between mathematics and the Brian. Physical universe. When physicists study the universe, they rely heavily on mathematical equations to describe how nature behaves. These equations allow us to predict the motion of planets, the behavior of light, and the structure of galaxies across enormous distances. Most of the time, the mathematics works beautifully. The numbers remain well behaved, and the equations produce clear, meaningful predictions about the physical world. But sometimes something strange happens. Under certain extreme conditions, the equations stop behaving normally. Instead of producing ordinary numbers, they begin to generate quantities that grow without limit. In mathematics, when a value increases endlessly without reaching a maximum, we say it approaches infinity. In physics, these situations are known as singularities. One of the most famous examples appears in the theory of general relativity, the theory of gravity developed by Albert Einstein. According to general relativity, gravity is not simply a force pulling objects together. Instead, massive objects bend the fabric of space and time itself. Planets move around stars because they follow curved paths through this distorted geometry of space-time. For most situations, the equations of general relativity work extremely well. They accurately describe the motion of planets, the bending of light near massive stars, and the expansion of the universe. But when gravity becomes extremely strong, the equations begin to predict something extraordinary. If a massive star collapses under its own gravity, it can form an object known as a black hole. At the center of a black hole, according to the mathematics of general relativity, matter is crushed into an incredibly small region where density and gravitational curvature increase without limit. The equations suggest that at the very center lies a singularity, a point where quantities like density and space-time curvature become infinite. This prediction creates a serious puzzle for physicists. Infinity in mathematics can be handled carefully, but in physics it usually signals that something has gone wrong with the theory being used. When an equation predicts an infinite density or an infinite gravitational field, it often means the model has reached the edge of its validity. In other words, the mathematics is telling us that our current understanding is incomplete. Physicists suspect that the singularities predicted by general relativity are not truly physical objects where infinite quantities actually exist. Instead, they may represent places where our current theories break down because they do not include all the necessary ingredients of reality. One reason for this suspicion comes from the fact that general relativity describes gravity on very large scales, while another theory, known as quantum mechanics, governs the behavior of matter and energy on extremely small scales. These two theories are both incredibly successful in their own domains, but they do not yet fit together perfectly inside a black hole. Conditions become so extreme that both gravity and quantum effects should be important at the same time. Unfortunately, physicists still lack a complete theory that successfully combines these two frameworks. Many researchers believe that a future theory of quantum gravity may eventually resolve this problem. Such a theory would describe space-time itself at the smallest possible scales and could reveal that singularities are replaced by more complex physical structures rather than true infinities. Some proposals suggest that space-time might become quantized at extremely tiny distances, preventing densities from becoming truly infinite. Others explore ideas in which black holes connect to new regions of space-time or undergo quantum transformations that eliminate the singularity altogether. Although these ideas remain theoretical, they illustrate an important principle in physics. Whenever infinity appears in our equations describing nature, it often signals that our current description has reached its limit. Instead of proving that infinities physically exist, singularities may act more like warning signs pointing toward deeper laws of the universe that we have not yet discovered. The study of black holes continues to push our understanding of physics into new territory. Observations of these objects, including images captured by the Event Horizon Telescope, allow scientists to test ideas about gravity under extreme conditions that cannot be reproduced on Earth. As our knowledge improves, physicists hope to uncover a more complete theory that explains what truly happens at the centers of black holes and whether the infinities predicted be your current equations are real features of the universe or simply mathematical signals marking the boundary between what we know and what we have yet to understand about the deepest structure of reality, where gravity, space-time, and quantum physics meet under conditions so extreme that the familiar rules of nature may transform into something far more complex than the equations we currently use to describe the cosmos, where infinity appears not as a physical destination, but as a clue that the story of the universe is still unfinished and waiting for new ideas to reveal what lies beyond the limits of our present theories. When scientists talk about infinity in the context of the universe, they are not just discussing mathematics anymore. They are asking a very real physical question. Is the universe itself infinite? Or does it have some kind of boundary or limit? At first glance, the universe certainly feels infinite. When we look into the night sky, the stars seem to stretch endlessly in every direction. Telescopes reveal more galaxies the farther we look, suggesting that space might continue forever. Modern cosmology began to seriously address this question after the discovery that the universe is expanding. Observations by astronomers, such as Edwin Hubble, showed that distant galaxies are moving away from us, with more distant galaxies receding faster than nearby ones. This discovery led scientists to the idea that the universe began expanding from an extremely hot and dense state in an event known as the Big Bang. If the universe has been expanding for billions of years, that raises an interesting possibility. Perhaps space itself extends infinitely in all directions, and we can only observe a small region of it. In that case, the universe might truly be infinite, stretching beyond any distance we could ever reach or observe. However, cosmology does not yet give us a definite answer. One complication is that we can only observe a limited region of the universe. Light travels at a finite speed, so we can see only as far as light has had time to reach us since the beginning of cosmic expansion. This region is called the observable universe. Its radius is about 46 billion light-years, which already represents an unimaginably large volume filled with galaxies, stars, and cosmic structures. But beyond that boundary, there may be vastly more space that we simply cannot see. The universe outside our observable region might continue forever, or it might eventually curve back on itself in ways that are difficult to visualize. Cosmologists often describe the geometry of the universe using ideas from the theory of general relativity, developed by Albert Einstein. In this framework, the distribution of matter and energy determines the overall curvature of space-time. Depending on how much matter exists and how it is distributed, space can have different large-scale shapes. One possibility is that space is flat, meaning that it extends infinitely in all directions without closing back on itself. Another possibility is that space has positive curvature, somewhat like the surface of a sphere. In that case, the universe could be finite, but without boundaries, just as the surface of the Earth is finite, yet has no edges. There are also more exotic possibilities involving complex topologies where space loops back in unexpected ways. In such scenarios, the universe might be finite, but still appear extremely large, because light can travel through complicated paths before returning to its starting point. Modern observations of cosmic radiation, including measurements of the cosmic microwave background, suggest that the geometry of the universe is very close to flat. A perfectly flat universe could be infinite, but it could also be extremely large, while technically finite. At present, the data cannot distinguish between these possibilities with absolute certainty. This uncertainty leads to a fascinating philosophical question. Infinity works perfectly well in mathematics, where numbers can extend forever without contradiction. But in physics, infinity often appears only as a limit or an approximation rather than a measurable physical quantity. The universe might be infinite, or it might simply be so vast that its true size lies far beyond anything we could ever observe. From our perspective, those two possibilities may be practically indistinguishable. Physicists such as Richard Feynman often emphasized that science does not claim certainty where evidence is incomplete. Instead, it builds models that match observations while remaining open to revision when new data appears. So when we ask whether infinity truly exists in the cosmos, we are really asking how far our observations can take us and whether the universe eventually reveals a boundary or continues expanding endlessly beyond the limits of our view across distances so enormous that even light traveling since the beginning of cosmic time has not yet had enough time to cross them, while the structure of space itself continues stretching outward through billions of years of expansion, leaving us with a universe that may be finite or infinite, yet always vast enough to challenge the limits of human imagination and scientific understanding as we continue searching for clues about the ultimate size and shape of reality itself, beyond the horizon of the observable cosmos, where infinity remains not just a mathematical concept, but one of the deepest mysteries in modern cosmology. So when we ask whether infinity truly exists, we step into one of the deepest questions in science. Mathematics allows us to explore endless numbers and structures through ideas like mathematic, infinity, while physics confronts strange possibilities such as singularities inside black holes and the enormous scale of the observable universe. Yet the real universe may or may not actually contain something truly infinite. What makes this question so fascinating is that it sits right at the boundary between mathematics, physics, and philosophy. As thinkers like Richard Feynman often reminded us, the beauty of science is not just in finding answers, but in discovering questions that challenge how we think about reality itself.